All right, so in this next segment, we're going to be talking about chemical equilibrium, and we'll discover there's a lot of relationships that apply once you let a chemical system reach to equilibrium. You can find out a lot of information about them. There's a lot of constraints that are placed on them. So let me share screen for a second. The learning objectives in this segment, we're going to be able to describe what happens to a reaction at long times once it reaches equilibrium, and we'll define that a little more carefully. Be able to write down an expression for the chemical equilibrium constant given the chemical equation, and be able to calculate equilibrium constants from equilibrium concentrations and vice versa. Okay, so for the easiest way to think about equilibrium, I think, is in terms of kinetics. There's other ways to get at it, but we're going to think about it in terms of the kinetics. So equilibrium, it's important to remember, is dynamic. Molecules don't stop moving when you reach equilibrium, but you have a constant exchange of reactants and products that has reached some steady state. All the reactions are still going just as fast as they were at the beginning, but the forward and reverse reactions have equal rates. So there's no net change in the amount of reactants and products. Each individual molecule is going back and forth between the two, at a rate determined by the kinetics of the problem. But if you look macroscopically, you'll just see an amount that doesn't change. To examine the equilibrium state, a common reaction that's used to illustrate this is N2O4, which is colorless, decomposing to NO2, which is brown. So what you can do is set up a reaction to this and look and see how the colors changes. We won't actually do this because chemicals are a little bit toxic, but it'll describe the concept as well. And what an important part about this is that usually under most conditions, this is not an equation where it's all to one or all to the other. You actually have both species coexisting at the same time. Okay, so let's look at what would happen over time. So let's say we start out, and we start out, this up here is the N2O4 rate. So we've got the N2O4 rate up here. And initially, let's say we start with just N2O4. So the rate of the forward reaction, N2O4, there's a relatively large consumption of N2O4 at the beginning because the reaction has just started. So, but as N2O4 is consumed, the rate of the forward reaction decreases. There's less N2O4, and so therefore you get a slower rate going forward. Now let's look at the opposite rate. The rate of N2O increase. So at the beginning, there's no N2O. So you have all N2O4, and you get a lot of N2O being produced. But over time, as you get more N2O, then you get a lot of conversion of N2O4 back to. So you get a lot of conversion of NO2 back to N2O4. Right at the beginning, you can't have any because there is no NO2 to undergo the reverse reaction to N2O4. But as time goes on, there's more and more N2O. And so what we get is that eventually we reach an equilibrium where the forward and the reverse rates are the same. And remember, these are not the amounts. This is the rate of, here's the reverse reaction, which starts out 0 and gradually gets larger over time. And here we have the forward reaction, which starts out high and gradually slows down until the rates are equal. When the rates are equal, there's no net production of N2O4 or decomposition of N2O4. It remains approximately the same. Now, the rate is increasing more rapidly. Right? The rates are always related because the forward rate and the reverse rate are related stoichiometrically. So that's generally what you see. So that is the dynamic equilibrium, where the rates keep changing to adjust to the concentrations until an equilibrium is reached. Okay. So equilibrium, as we said, is a dynamic, a constant change of reactants and products that has reached a steady state. So let's look at what relationships come out of it. We have this rate forward equals rate reverse, which indicates there's a constraint on the system. There's an equation the system must satisfy, which means we can get some information out of that. So let's start with considering the equilibrium of an elementary reaction step. So this is like a second order bimolecular reaction. A plus B reacting to reach C, and then in the reverse direction, it's first order. We're assuming it's an elementary step, so we can figure out the mechanism just by looking at the stoichiometry. So the rate of the forward reaction, that's going to be some constant times the concentration of A times the concentration of B. The rate of the reverse reaction, well, will just be some rate constant, we don't know what, times the concentration of C. And at equilibrium, then the rate forward and the rate reversed have to be the same. And so we can mathematically set them equal to each other. And actually, let me add a little bit more math here. So if the rates are equal to each other, then we can take this relationship and say, okay, great. I'm going to divide both sides by KR. So we have KF over KR. And I'm going to have concentration over here. And I'm going to divide both sides by concentration of A and concentration of B. So this is interesting because notice this relationship here, KF over KR, that has nothing to do with the equilibrium constants, right? Nothing to do with the concentrations, right? That's the same no matter what the concentrations are. So we could just call it an overall reaction K, and that's constant. So we can see, we can write at equilibrium, certain combinations of the reactants have to be constant. So, so each equilibrium is characterized by a distinct ratio of reactant and product concentrations known as the equilibrium constant. I just showed this for elementary reactions where we can actually just read off the mechanism from the stoichiometry. It turns out to also be true for multi-step reactions as well. It's not, it's a general equilibrium statement. It's a little more complicated to prove if you have multi-step reactions, but showing how it works for elementary reactions, it helps illustrate the idea that if the forward and the reaction rate are equal, there are certain combinations of the reaction coefficients that must be equal. So K, it does depend on the temperature. Different temperatures, the forward and the reverse reactions will have different rates. So you will have different equilibrium constants at different temperatures, but it does not depend on the concentration. So if you have initial condition, if you have initial concentrations, you can look over time how they behave, and the equilibrium reaction will be determined solely by those ratios. It won't be determined by anything else. So if you know the equilibrium constant, you know how the system is going to behave at equilibrium, assuming it stays at the same temperature. Okay, so that is that's the main concept that we're going to be playing with. Is if we know the equilibrium constant, what more can we say about the system? So equilibrium and stability of final concentration. So for example, if I have, my N2O4 and my NO2, and now I'm looking at the concentration of each of these as a function of time, I start the reaction with, say, no NO2 and 0.04 molar N2O. It reaches equilibrium according to the equilibrium constant. What if I start from another amount? If I start from 0.08 NO2 and 0 N2O4. Now it's important here, we have to start so there's an equal amount of stuff in the system. If we start with a different amount of stuff in the system, we'll end up with different equilibrium. But in this case, since we started out with the equivalent amount of NO2, right? So 0.4 molar N2O4 is the same amount of total material as 0.08 molar NO2, then if we start from that other initial point with the same total amount, we will reach the same equilibrium. So it doesn't really depend on the equilibrium conditions. Obviously, if we have less stuff, there'll be less stuff at equilibrium. But assuming that we have the same total amount of reactable material, then we'll reach the same equilibrium every time, no matter how much of it is reactants and how much of it is product.